All right, this is our last little video on thermochem. Thanks for gutting it out with me, sticking with me. This is the third video. You can go back and check out the first two if you want. Last video we talked about whether reactions are spontaneous or not using Gibbs free energy. This guy is talking about even if a reaction is spontaneous, there's still a few factors that have to happen in order for a reaction to take place. And this is called the collision theory. And so there's two things that have to happen. In order for a collision to work and have a reaction occur, you have to have a collision. Things independent of one another, if they're sitting independent of one another, they're not going to react. They have to run into each other in order to react. When they collide, they must have enough energy. So they have to be energetic enough, and they have to be oriented in the right way. And so the hallway analogy is this. When we're walking around the halls, we walk so slow that even when we bump into each other, we're not bumping into each other hard enough to hurt anybody, right? We bump shoulders and we say, my bad, and we keep walking, right? Not only that, but we're not even oriented in the right way, right? If you bump shoulders with somebody, even if you're moving fast and you bump shoulders with somebody, it may hurt, but you're not going to get permanent damage or having a cut that gushes blood as a result, because you're oriented in a way that you're not hitting each other in a way that's going to harm you. So the same thing applies to particles. If I have, make sure I can fit this on here. If I've got particles that look like this, and they move really slow towards each other, then those atoms there are surrounded by electrons that are repulsive. And so if we bring them together really slowly, then those electrons are going to repel them really slowly away from each other. And so they're not moving fast enough to have the ability for the electrons here to interact with that nucleus over here. Those other electrons are going to repel it before they can interact with the other nucleus. So they've got to hit each other pretty hard. Not only that, but in this case, if those two dark circles are trying to react with each other and they run into each other this way, those circles don't have an opportunity to touch each other, and so they don't have any ability to react. So in order for this reaction to take place, you would have to have those particles run into each other and have those two little dots be facing each other so that when they run into each other, they have enough energy and are correctly oriented. Good. And if you did that, then you could have those things turn into a situation where the little dots end up bonding together and those two bigger atoms become independent, right? You could change their structure. That's what a chemical reaction is. But they have to be able to penetrate past each other's electron clouds in order to get that done. So right orientation, right energy. Good. So in terms of humans, right, since I used the human analogy a second ago, this is why offensive linemen in football and defensive linemen in football end up having brain problems when they get older, because they line up, they're big and strong and full of energy, they're fast, right, and they line up so their heads are pointed right at each other, and then they snap a football and then they just jam each other's heads as hard as they can, right? That is the correct orientation to cause brain damage, and they have so much energy that when they hit each other, it causes a reaction to occur. That's a very sad analogy, but it is a good analogy for there to be brain damage. If they lined up with their heads towards each other and they walked over there and tapped heads, they would be just fine, right? But they have so much energy and that orientation where their heads are towards each other that they can cause a reaction to occur. Okay, that energy that's required for those guys to react is called activation energy. It's the minimum energy required for the reactants to reach what we call the activated complex. The activated complex is the moment those guys run into each other and start to reorient their bonds. And I'll show you what this looks like in a visual here in a second, what we call an energy diagram. So the activated complex is where the old bonds are broken and the new bonds are formed. That's how we describe it. It's a transitional structure. Old bonds broken, that's the important part here. Old bonds breaking, new bonds forming is what happens at the activated complex. We got one little slide left. So this is how we label the activation energy, EA. E subscript A is activation energy. The peak of these energy diagrams or reaction pathway graphs is the activated complex. And then usually they give us some kind of energies associated with these things. So this is how these graphs look. You've got reactants going to products on the X, and on the Y-axis you have energy. And so this delta E, or sometimes you'll see it as delta H, right? The energy for the reaction is talking about from the start of the graph to the end of the graph. That's our change in energy. Good? Would this delta H or delta E, would that be endo or exothermic? Because of that negative sign, this would be an exothermic reaction. And so the way I start these all the time is at that little dash, it's arbitrary where you stick it. I put a 0. That's my starting energy. There is 0. From the start to the finish, going in the forward direction, going from left to right, I end my graph at -10. And so this is where my graph will end, is at that -10. So I start at 0, I go to -10. Now, when there's an exothermic reaction, there's not a, it goes right from 0 to -10. There is an activation energy, the energy required to get that reaction to take place. Like if you have a match, you don't just hold the match up and then it spontaneously bursts into flames. What do you have to do to get that match to light? You have to take it and you have to rub it across something, right? Add some friction. And so that friction is the activation energy that causes that match to light, and then once that match lights, that's an exothermic reaction, then the heat comes back down. So when we look at the activation energy for this reaction, it takes 40 kilojoules per mole, which means to get to the activated complex, you have to go up 40 from the starting point, and those are our 3 points. The 0 you always start with, the final point, and then that activated complex. And so our graph looks like this, where to get that reaction to react, we have to put in that activation energy. Here is where the activated complex is. That's right when you rub the match and it starts to light. That's here, where old bonds are broken and new bonds are formed. And then that energy is released on the back side of that graph. So our delta E for the forward reaction, that's this part. This is delta E or delta H, that's -10. From the start to the peak of that graph, that is what we would call our activation energy. So EA would be 40 there. All reactions are reversible. So technically, if you went from products and you put in 50, you would call that the activation energy for the reverse reaction would be 50 to cause it to go back to the activated complex from products to reactants. That would be the reverse reaction. Good. This reaction overall, because we started higher than we finished, would be exothermic. Good. So if it's an endothermic graph, our graph would have looked like this. Our graph would have started down here, it would have gone up, and then it would have finished higher than it started. That would be a positive delta H because we were from 0 to plus whatever, 50 or 60. Good? But you always have some kind of activation energy. They're always bell curve looking things where the activation energy is higher than both the starting and finishing points on those things. Good? Here, that's our delta H. Or delta E, our activation energy would be from start to the peak. That would be our EA. The only other thing that you see in these activation pathway graphs or these reaction pathway graphs is sometimes you'll see a catalyst. We talk about a catalyst speeds up a reaction. In reality, kind of the grown-up way to say that is the catalyst lowers the activated complex. It takes that activated complex and lowers it down. So the dotted line serves as my catalyst. What does that mean? It means those collisions need less energy to react. So the reason that the reaction speeds up is because more of the time things are colliding, they're colliding with enough energy in order to reach that activated complex because we've lowered it, that activated complex. Good. You'll have some stuff to work on the next couple weeks over Thermochem. I hope that makes some sense. Don't hesitate to ask if you got questions along the way. Talk to you later.